Hi, everyone. I'm Akanksha, and I am the Content Marketing Manager with Delta Q Technologies, part of the Zappi Group of companies. I'd like to welcome you all to our last session for the Future of Electrification Conference. Please remember that this session is also being recorded and will be available to watch on demand following this session. If you have any questions during the session, please add them to the Q&A tab, which you can find to the right of your screen. Note that your questions will be sent privately. With that, I would like to introduce our speaker. I'd like to welcome John Wathen from Inventus Power, who will be speaking today about revolutionizing vehicle ancillary equipment with lithium battery technology, a trending path to sustainability and efficiency. Welcome, John. Please take it away.
Thank you, Akansha. Thank you again to the Zappi Group for hosting us. Again, I'm John Wathen with Inventus Power. Today I'll be presenting about revolutionizing vehicle ancillary equipment with lithium batteries. A little bit about myself. I'm a senior applications engineer at Inventus Power. I've been with the company for about 5 years, but I've been in the power electronics industry for over 10. I actually used to work assembling electronics when I was in high school even. I'm based out of Ohio on the East Coast. I've been a maker all my life. I'm a hobbyist. I like to repair things around the home. So I really have a close attachment to this industry because I like to use a lot of the equipment that we kind of see with it. So thanks again for coming, and with that I'll go right in. Quick introduction on the agenda here. We're going to go over kind of Inventus Power, go into battery powered ancillary equipment systems, or AESs. I'll cover some industry trends and market drivers that we see, some application examples, some approaches to electrification, and then some benefits and some common misconceptions or challenges that you can see. And then we'll go to a summary and Q&A session. So company overview of Inventus. We're a global leader in advanced battery systems. We specialize in designing and manufacturing high quality, reliable, and innovative power solutions for a broad range of applications. We're a USA headquartered company with 4 global factories, over 3,000 employees. We do all of our own in-house design, testing, and certification. And we have over 2 million products shipped monthly. We're a trusted partner to the world's leading OEMs across all business segments. We're always at the forefront of the transition to new battery technology, and we're currently leading lithium-ion electrification in emerging xEV markets. Our global footprint is our U.S. headquarters. Again, we have an R&D technical center, manufacturing and sales and service here in Illinois, United States. We have manufacturing in Tijuana, Mexico, additional manufacturing in Brazil and Qingxi, China. And then we have sales and service in South America as well as Europe and East Asia. We have 2 additional R&D technical centers, one in Doha, Qatar, and one in Guangzhou, China. So now jumping into battery-powered ancillary equipment systems, or AESs. We went over our global reach there. Some of the major concerns driving this adoption is global emissions. The global emissions by sector is over here on the right. You can see the transportation sector makes up 29% of the global CO2 emissions. 70% of those transportation CO2 emissions are from road transportation. And then 20%, we're looking at 27% of road transportation emissions from medium and heavy duty trucks. 30% of those medium to heavy duty trucks have onboard ancillary equipment. So we've identified that approximately 2 to 3% of global CO2 emissions are from medium to heavy duty trucks with ancillary equipment. That's 0.8 to 1.2 billion metric tons of CO2 annually. Some of the challenges for this equipment sector or this vehicle sector with full electrification is that an electric chassis, if you wanted to take a vehicle, for example, a garbage truck, takes about 50 gallons of diesel fuel. For a garbage truck, that energy density is 2,047 kilowatt hours or 2.047 megawatt hours. Converting that out to the diesel with a diesel engine theoretical efficiency of 55%, and then an electrical system efficiency of 93%, we can actually extrapolate that it would take 1,211 kilowatt hours of electrical energy needed to move a vehicle like a garbage truck around on a normal route length. If you look here, at the right, we're making an analogy here with the weight. That's 4,000 kilograms of battery at 300 watt hours per kilogram, which is a very, very aggressive, efficiency metric. So that's 8,800 pounds of battery. That's the weight of an empty 40-foot high shipping cube container. And so in its current state, the practicality really only exists for powering the ancillary systems using electric solutions, which is what we're kind of covering. So going over to our target markets and applications here, we've got small to mid-sized vehicles and systems with electrical and mechanical equipment. The power is provided to the hydraulic pumps, vacuums, compressors, actuators, solenoids, etc., using either the engine or an extra engine that's powering these things. Um, so some examples of applications that we see: uh, refuse collection. The lift and dump operations are light duty but frequent, and it's often performed when the vehicle is stopped. So compaction is higher demand, but that duty cycle is less frequent. So in either case here, you can achieve idle reduction or elimination, because you don't have to be running the vehicle's engine while these other functions are operating. A bucket truck, you have very similar kind of requirements. The engine does not need to be running when the crane is being operated. And in some jurisdictions, that might even not be allowed, because you don't want to cause a safety issue where the vehicle could drive away. Noise reduction can also be measurable in some of these applications. Idle reduction can be achieved here as well. For the case of a refrigerated truck, your compressor is light duty. It does not require a significant amount of energy to power. It will be independent from the drivetrain power source, so you can leave the refrigerated cab, or leave the refrigerated trailer behind, take the cab somewhere else, and move another trailer or something like that while the refrigeration still operates. This also allows for idle reduction to be achieved while you're actually moving, because you can stop the engine of the vehicle itself while the refrigeration still continues to work. And then for a more aggressive application, more corner case, a cement truck, you have a motor that turns the mixing drum. That does not require necessarily a significant power source to keep going once the inertia is built up, but it might require a high peak current to start it up. You also can benefit from some benefits here, such as noise reduction and idle reduction as well. Some additional examples of small to medium-sized and ancillary equipment systems that we have identified would be anything with an electric power takeoff and EPTO, being like a boom, a crane, any sort of equipment that attaches to the truck. Equipment that's commonly seen on a truck bed, that's more accessory equipment, such as a welder or a compressor. Vacuums and pumps, that's more trailerable type equipment. And then winches and cable hoists, you see that on like a loading platform truck. And then any equipment that's trailerable as well, like a chipper, mulcher, vacuums, lights, and gensets. So a lot of potential for a lot of opportunities here for the electrification. So another quick study here that we've looked at for emissions reduction is an electric side loader on a garbage truck requires approximately 50 kilowatt hours of energy. That accounts for about a 30% CO2 emissions reduction for medium to heavy duty trucks. It's a 1% reduction in total global emissions. There's also significant criteria air pollutant reduction, such as nitrogen oxides and sulfur oxides, by eliminating small engine use on some of the other accessories that we talked about earlier. So why ancillary equipment systems? There's a lot of incentives that are being offered and requirements that are being put into place by regulatory agencies, the European Commission, the EPA, the California Core incentives, and requirements are all driving a lot of this electrification that we're seeing. Some of the other reductions on emissions that we see is not necessarily environmental emissions, but noise emissions. In a neighborhood, you'd like to see a vehicle be quiet so that it doesn't, or in a consumer space, you'd like to see a vehicle be quiet so that it doesn't disturb the occupants. It can also be a very good address safety concerns for the users of the equipment. If you don't have to have as intense hearing protection, or if you don't have to wear hearing protection at all, you can hear somebody warning you of a safety issue and try to and then that will reduce safety concerns. And then we also reduce uh, total cost of ownership, and maintenance intervals are significantly reduced. You're getting rid of a lot of moving parts in these cases. We all know that an engine has many moving parts, whereas an electric motor has very few. Um, so that application kind of directly translates to this as well. Another study here on the refuse collection example here, we see that with a diesel chassis, hydraulic body, standard garbage truck, you get the very good range of about 100 plus miles per day. You can hit 1,200 plus homes a day. The payload can be very high, and the CO2 emissions, and charging infrastructure, we're not really worried about that for that case. But when you go over to when you start doing electrification on just this application, if you electrify the entire system, you sacrifice a lot because of kind of what we discussed earlier, where the vehicle weight is increased, and you can't make as many stops. So the benefits of doing an electric ancillary system, or electric side loader in this case with a diesel chassis, would be you maintain your range for productivity, you have your increased payload and efficiency, significant emissions reduction, you lower the battery weight and cost when you're only having to worry about electrifying the ancillary equipment, and you lower your charging infrastructure requirements. You don't have to pull this vehicle up to a large charging station in order to maintain it overnight. Let's go to some types. So pulling up to charging stations is kind of important. We will discuss that a little bit. Some types of system integration, cover that as well here. So our first system that we're imagining is an independent electric ancillary system. This has like trailerable type solutions, and solutions that are more modular and flexible, that can be either bolted on or temporarily attached to a vehicle system. So we have a low level of integration here because we're only really focusing on the ancillary equipment system and any sort of mechanical attachment points to the vehicle if desired. But this is a flexible platform. You can charge it on site or in storage, but the vehicle that's used to transport it does not need to be attached. You can charge it with the vehicle while it's transported, why we've got the optional dotted line here to the vehicle powertrain. And then some of the benefits as well of a system like this is that it kind of eases certification concerns on this accessory/trailer, because it could be considered much easier to certify. This is a prime candidate for noise reduction opportunities. Most applications in this space are used pretty exclusively in residential or light commercial areas where noise reduction would be most beneficial. Going to the next type of system, this is kind of where we see the garbage truck application come back into play. This is a medium level of integration. You're really bolting on the ancillary system directly to the vehicle chassis. It's more of a permanent or modular type integration to the vehicle. You can charge the EAS on site or in storage in this case as well. But you can also use the vehicle to charge the battery system also. The certification challenges here might be a little bit more difficult depending on how the standards are interpreted. Could require certification more on the vehicle level because it's considered a permanent install. This application, or this type of system, we also see as a prime candidate for noise reduction opportunities, because again, a lot of the applications that we see this in are, residential and light commercial. And then finally, we have kind of a mechanical hybrid ancillary system. This is like a plug-in hybrid type of solution that we've imagined, that's kind of where you can use the vehicle's powertrain to power the ancillary equipment, but you can also select between that or the electric power system. This can be very useful if you're stuck in a remote situation where you need the equipment to operate, but you run out of charge on the battery, or a scenario where the equipment might require an extremely high load in order to operate only for a short amount of time. And then you can switch over to the electric power, such as our example earlier with the concrete mixer. The certification challenges and integration challenges here would be quite high, because that you have essentially you're keeping all the mechanical linkages, and you're also increasing the integration level as well. This is really ideal though for these corner case duty cycles or applications where the significant load would be required for one system of the ancillary system, but not another. Cement mixer drum would be a subsystem of the whole cement truck, but the cement chute would be a separate subsystem where the actuators could be exclusively electric. A crane boom arm would be another example on the back of a truck, where the arm might need to be powered by a higher power solution, but the cable winch for that crane boom arm could be powered by an electric solution. And then you have something like a chipper mulcher where you're loading the uh, wood into the chipper mulcher with an electric powered crane, but the chipper mulcher might need to be powered by another solution. So going over kind of some of these solutions that I described, we've kind of developed an electrification conversion path for kind of the trends that we see in this market. Fully electric actuators are being a lot of interest is being driven around these. The advantages here are position, repeatability. You get precision that's unmatched by hydraulic systems. The repeatability, when paired with a capable system controller, means that you could program the actuator to do redundant tasks and really eliminate the need for some of the training that you might have to provide to a user or to an operator. There's feedback to the system controller, which is able to be provided so you could have force or stall warnings, so you can basically ensure the safety of your equipment and of your operators. Cleanliness advantages here with the electric actuators. You're eliminating the hydraulic fluid requirements, so you're not having pumping opportunity for leaks, etc. And then you're reducing wear and tear on the vehicle system. A lot of seals, hoses, fittings are being eliminated by this electric actuator system. With a hydraulic electric pump motor system, you have the capability to retrofit to an old hydraulic system that's powered by a traditional PTO, where you can use now an EPTO type of situation. This provides the capability as well for on-demand pressure, where you don't have to keep the engine running, so you can eliminate, that you have idle reduction there, you reduce your fuel costs, reduce your emissions. It's also variable speed. So whereas it might be difficult to vary the speed of a traditional PTO engine-powered hydraulic pump, you could vary the speed of an electric motor quite easily with an adequate control system. And this can basically increase or decrease the pressure in the hydraulic fluid to increase or decrease the speed at which the actuation is occurring. So it also enables some additional precision out of a hydraulic system that you wouldn't see traditionally. And then we have less wear and tear. Again, no transfer case, no drivetrain adapters, no clutch, etc. It's all a lot of benefits for maintenance and ROI. Application specific example, again, we kind of touched on this earlier as well, is the cement mixer. You have the drum the drum motor where you have high gearing, low RPM. It's an ideal use case for electrification because it's light loading on the batteries once that drum gets spinning. That inertia kind of keeps going and you don't have to really keep it going as much. Can allow for a greater vehicle platform flexibility. You have a trailerable option now with a cement truck, which is kind of something that's unheard of. You can leave the mixer at the job site, take the truck that delivered it to the concrete plant and pick up another load while that cement is being delivered to the task here. So you're really saving a lot of time, increasing productivity on the job site. Noise can be significantly reduced here as well. Hearing loss, this is another very important thing if you're constantly working next to machinery like this. And then you have idle reduction opportunities as well here too. Going on with the electrification conversion path, we've got some solutions by our presenting host here, Zappy Group. Motor control, we're seeing a really drive to precision motor control systems and solutions where we want to be able to have the sensitivity to measure if there's a load or stall. That'll reduce the wear on the equipment itself. We want to be able to program repeatable functions so that an operator doesn't have to be trained as much. The feedback can be given to a control system or something like that as well. You have that repeatability there. Soft start capability on motor controls are really important on the more modern motor control systems. This is a feature that's very, very useful, especially for lithium-ion battery packs. It enables you to power on the system slowly so that you don't have inrush current that trips traditional lithium-ion battery BMS. And then we have quick startup and shutdown. This is also an important key safety feature. If you need to be able to start up and operate the equipment quickly, you can do so. Or if you need to shut it down quickly, you can also do that. Then we have our onboard AC/DC chargers. This is there's some advantages here. You have standard electrical connections, um, you know, IEC plugs, NACS plugs. It can be powered by your traditional electrical infrastructure. It doesn't require a special charging station or a high current plug. You have universal voltage input, so you can you can go across many different voltage solutions here with this. Um, your upgrade path is already present if your faster charging is desired with an NACS plug. Uh, it's upgradable it's there. So, and then you can communicate with the battery system to ensure balanced and reliable charging. You can also communicate with the motor controller and the system controller to achieve optimal performance where the charger acts is part of the system as well and can keep the end user operator informed of where the charging process is. An additional part of the upgrade path that might be necessary would be a high current alternator. It might be required to kind of keep the tank full of the batteries. It doesn't power the equipment directly. Kind of just maintains the battery level so that it's always ready to do the work. When properly implemented, a new alternator type solution can provide voltage to the batteries only when it's needed. This is kind of like more of a maintenance versus opportunity charging, argument and benefit here. This can reduce you have idle reduction here on the vehicle, reducing operating costs and increasing efficiency and reducing emissions. Plus, you can have efficiency boosts for the vehicle system, which you can enable further optimizations of the vehicle platform at that point. So, touching on some of the challenges and benefits here. We've gone over a lot of the solutions. We got some common misconceptions first that I want to clear up. With the duty cycle, we see that many light to medium duty AESs cover a broad range of applicable duty cycles. Some might require a small amount of energy all of the time, and some might require a lot of energy only a short amount of time, and that's more of like an on and off type of duty cycle. So in a lot of cases, the applications are all fit within a scenario where energy storage, a lithium solution makes a lot more sense. It can be a challenge to right size the battery system for the requisite balance of demand and capacity. And really, it's as well, the duty cycle is dependent on the OEM's capabilities to test, qualify, and optimize their existing systems. That way, the conversion goes smoothly. When we look at integration challenges, we see that that includes like dealing with control systems and environmental operational concerns, such as temperature or exposure to other adverse conditions. You have the subsystem compatibility and complexity, which can be managed with proper design practices. Not all subsystems are fully compatible. We've covered a lot of the potential retrofit solutions, though, that showcase the flexibility and ease of integration when it comes to this, though. So basically that ease of integration and system optimization can be really optimized if you have clearly communicated system designs and requirements. So the severe environmental conditions that we see not only be weather related, but also in relation with the integration to where or how the vehicle is stored, or even where the batteries are installed in the target application. Some other common challenges or misconceptions here: it might be difficult to realize the benefits. You can reduce or eliminate emissions by eliminating engine idling or allowing the engine to idle where it would otherwise be heavily loaded. That could be so it can be hard to capture the benefits of this without a data-driven approach. Depending on charging infrastructure, it can provide zero emissions opportunities where this would normally not be possible. If you have charging infrastructure that's powered by a zero emissions source like solar or wind, you can really realize a lot of benefits here. You get some increased upfront costs to the end user. The cost of the battery and the other subsystems would add costs to the application, but the maintenance can be significantly reduced. So it's difficult to realize what the return on investment is there without having a good integration partner. And then certifications. Testing and certifications will add costs to the development. Certifications might be difficult if the entire vehicle platform is being electrified, like we discussed earlier with the shipping container weight. It's also kind of doesn't really make sense, but it's easier. So it's easier to target a bolt-on auxiliary type system for certifications. Again, a lot of these challenges and misconceptions can be overcome by selecting a good integration provider. Retouching on a lot of the benefits that I've touched on here. We're reducing your engine idling emissions and noise. It's helping you to achieve environmental, social, and governance goals. It's also improving improvements towards regulatory and compliance requirements if there are any. And then you have another one that's really important again is noise reduction. When you're reducing the noise, you're reducing the concern or the irritability of the people around the equipment, and then you're also increasing the level of safety in operating that equipment, or removing the need for safety PPE such as hearing protection, and then you can hear people talking over the equipment. It's improving fuel efficiency by eliminating the engine idling or idle reduction or elimination. And then lowering the maintenance cost. Again, we touched on this, decreasing the maintenance intervals, and we have less replacement parts from all the moving parts. And that results in an additional lower total cost of ownership. And then we can use traditional charging infrastructures to charge the battery. We don't have to have a special charging station, but if it's desired to charge faster, that can be done as well. So thanks a lot for going over all these integration challenges, benefits of ancillary equipment systems. Again, I really appreciate Zappy Group for hosting this presentation. My name is John Wathen with Inventus Power. If you have any questions, I think now is the time. Thank you again.
Hi, everyone. So now this is where we begin our Q&A session. If you haven't already, please submit your Q&As in the tab on the right of your screen. We do have a few questions, so we'll run through them. And while we're running through them, you have the time to submit them. So the first question that we have, John, is, are there additional benefits that can be realized from electrification regarding Internet of Things?
Yeah, so when you have an electrified platform, Internet of Things becomes a lot more capable and available. You can get a lot of metrics from all of these controllers, the system controllers, the motors. You can use that to have fleet insights and maintenance scheduling. You can that increases your operational efficiency of your organization, and those gains, basically can be tied directly to the field diagnostics that you no longer have to perform.
Perfect. So another question that we had come in was, in what applications would fully electric actuators replace traditional hydraulic cylinders? Are fully electric actuators cost and space efficient?
Yeah, in a lot of applications, we see fully electric actuators replacing hydraulics. They can be much more space efficient, especially because if you're able to replace the entire system in a traditionally hydraulic system with electric, you're eliminating hydraulic reservoir, you're eliminating the hydraulic pump, you're eliminating the hydraulic motor there. In some cases, the actuator body itself can be a little bit bigger, but the overall advantages, I think, here significantly outweigh.
Okay. What is driving the conversion to lithium electrification versus using lead acid technology?
So lithium, definitely we see a higher ROI on the lithium. Cycle life is greater. So you're replacing batteries less. That's not only a lowered cost in the capital in itself, but also in the workforce to do the replacements. And you also don't have to maintain the lead acid batteries, so you don't have to water them. You don't have to make sure that the system is balanced. A lithium system is much more intelligent and does all that for you.
So, another question that we've come in is, what industries are you seeing first to adopt battery-powered ancillary equipment systems?
Definitely construction, lawn and garden, and outdoor power equipment, and refrigerated truck units. That's definitely where we're seeing a lot of the trend going for Inventus.
Perfect. So those are all the questions that we've had come in. With that, I would like to thank you so much, John, from the entire Zappi group for preparing this presentation and joining us for the Future of Electrification conference. I'd also like to thank all the audience for attending our conference. This is the last session and our conference is over. We do have all the sessions recorded, which you can watch on demand, and you can share it with your colleagues as well. And I really appreciate all the support we've gotten, and I hope everyone enjoys the rest of your day. Thank you, John, once again.
Thank you. Much appreciated.